Hello Year 12. Today we're going to look at Unit 8, which is periodicity. It's a short little unit all about the repeating trends and repeating patterns within the periodic table. It'll only take us one video lesson to get through this, and I'll set some questions. We'll have a little end of unit test on it as well. So, a little bit of a brain teaser to kick us off. What am I? I'm periodically the number 79. Long ago, some attempted to make me from 29, but learned it couldn't be done. If you add me to 80, I appear to be 47 temporarily. Pause the video, have a little think, and hit play when you're ready for the answer. It's actually gold is the answer, periodically the element number 79, and that's relatively straightforward to work out. However, there's a bit more to it than that. Because long ago, alchemists, which were really chemist is in the name, these were the forefathers of chemistry way back in the Middle Ages. People tried to make element number 79, obviously they didn't know it was element number 79, from copper, because copper has very similar properties to gold when you think about it. It's unreactive, it doesn't really react easily with water. It's a fantastic conductor of electricity, although I suppose the alchemists didn't know that. And then even if you look at the modern periodic table, copper and gold are in the same group, and copper is the atomic number 29. If you add gold to mercury, and this was known to the alchemists, then it appears to be silver, number 47, for a short time at least. So periodicity is all about repeating patterns, repeating trends within the periodic table. And the periodic table provides us as chemists with a very structured organisation of all of the various different chemical elements, and we can make sense of those chemical elements in terms of the physical and chemical properties, in terms of those repeating patterns. And you'll know from your GCSE studies, Year 12, that the historical development of the periodic table was something that was done over many, many years, and it gave us some models of atomic structure to provide us some good examples of how scientific ideas and explanations have evolved, have developed over time. And that's key to science, is that a model explains some behaviour, and if we come across some behaviour that isn't explained by a model, then we need to change our model to fit the facts. It's not that scientists lie, or that we're only giving you enough information to explain something. It's simply that as we learn something new, we have to adapt our model, adapt our theory to suit the facts. And these first two statements are lifted straight from your unit guide. So what are we learning about over the course of this very short little unit? A lot of this you'll know already, a lot of it's sort of revision. So we know that we can either classify an element as an S, P or D or F block element. And F block you don't really need to know terribly much about, but you do need to know about S, P and D block elements according to its position in the periodic table, which is really determined by its proton number, by the element's proton number. You do need to know about the physical properties of period 3 elements, and we'll revisit this in Year 13 and go into a bit of greater depth. But you need to know about the trends in the atomic radius, first ionization enthalpy, and indeed melting points of the elements from sodium through to argon. And the astute amongst you will realise that that will involve reviewing really atomic structure, these first two aspects which we covered in the unit atomic structure. And then in terms of the melting point, really we're thinking about structure and bonding, which was way back in Unit 3. Physical properties of period 3 elements. You need to also explain the trends in atomic radius and first ionization energy. Again, that links back into Unit 1 on atomic structure. And you need to explain the melting points of the elements in terms of their structure and bonding. Again, linking back into Unit 3. Here's a periodic table, or at least a very, very sketchy one. Mendeleev knew there was about 60 or so elements known to Mendeleev, And he wasn't the only person who was working on periodicity and trying to work out if there was an order to the elements and if he could discern anything about the chemistry and physical properties of the elements from laying them out in special ways. But ultimately, he figured out that there are repeating patterns in chemical and physical properties across the various different periods, what we now call the rows of the periodic table, rather than the columns, which are the groups. And the modern periodic table, and Mendeleev didn't know about protons, so he couldn't organise his periodic table in this way, but the modern periodic table arranges elements by increasing proton number. And we call the groups those vertical columns, and we call, as we know, the elements in a group have very, very similar chemical and physical properties because they have the same electron configuration in terms of the outer shell. So group 1 elements have 1 electron in their outer shell, group 2 elements have 2 electrons in their outer shell. And all the group 1 elements have very similar chemical properties, similar reactivity, and the group 2 elements have very similar chemical reactivity, as we know. Then we get to look at these rows then, the periods. The horizontal rows are called the periods. And that's where that feeds into this idea of Mendeleev, that in periods, those periods show repeating trends in physical and chemical properties. So just as we can think about the reactivity going down a group, we can think about the chemical and physical properties when we go across the period. Indeed, if we look at period 2, there are similarities between period 2 and between period 3 and between period 3 and period 4 and so on, with the exception of these guys here in the middle, the transition metals, which you'll come on to in year 13. And indeed, in this particular unit, we're going to look at period 3 as a nice little example of repeating patterns that repeat all across the periodic table. And indeed, we'll build on that in year 13 as well. So there are periodic trends as we go across the rows in the periodic table. And as you know already, you've got the S block here, because these all have S orbitals in their outer shell spheres. The P block over here, those dumbbells, PX, PY and PZ. The D block here, which have 5 orbitals, and we won't really go into those shapes too much because it goes beyond the scope of A level. And the F block, the actinides and lanthanides and actinides, which kind of sit on their own down here somewhere if you look at your data sheet. So we need to think about various different properties then. We need to think about the atomic radius, the melting point and boiling point of various different elements as well. How was the periodic table developed? What I'd like you to have a go for a bit of homework, guys, is to have a think about how the periodic table was developed. You'll have learned about Newlands and about Mendeleev during your GCSE studies, but they weren't the only people who had been working hard to develop a periodic table. There was Dobereiner, there was Moseley and Seaborg as well. And what I'd like you to do really for your own sort of information really is to create a little poster for a bit of reading around the subject and developing your chemical knowledge, which explains the contribution of each of these scientists to the development of the periodic table. If you could photograph it and send that to me, that would be even better. I can see what you've been up to. Periodicity then. You need to be able to classify the elements in SP and D blocks, not so much worried about the F block, but you need to be able to look at an element and say which block of the periodic table it is in according to its position in the periodic table. Hopefully that's something that you already know how to do. I've reminded you today, but that's something that I'm expecting you guys to know how to do from Unit 1 in terms of atomic structure. But you also need to be able to look at the properties of the elements of period 3 to illustrate periodic trends. You need to be able to describe the trends in the atomic radius, first ionization energy, melting point and boiling points of that period, of those period 3 elements from sodium through to argon. And you need to be able to understand the reasons for these particular trends in those properties. And that's what we're going to look at now. We know what a period is. A period is a row across the periodic table, and periodicity is the regular change of properties across period of the periodic table. And this pattern is repeated in different periods, so we can look at period 2 and we can compare it to period 3. Indeed, the properties will be very, very similar. Again, all of this is in your unit guide. I'd advise you perhaps at certain points to pause the video and add to your unit guide as you're going through. Okay, list the elements in period 3. Well, here they are: sodium, magnesium, aluminium, silicon, phosphorus, sulphur, chlorine and argon. And what's happening here, if we think about the electron configuration as you're going across period 3, is that you're adding electrons into the same shell. That means that the atoms are going to be of similar sizes. The shielding is the same. The nuclear charge is increasing though, but so there's a greater charge pulling on those electrons. And many of the properties depend upon these two facts. So whilst the atoms are of a similar size, they do vary somewhat. Sodium is going to be larger than chlorine, for example. But nevertheless, they're of a similar sort of size, and many properties depend on those particular two facts to do with the atomic radius and the nuclear charge, and linking in with shielding. Okay, so down the left-hand side here, I've got atomic radius, first ionization energy, melting points and boiling points. On the right are various different factors that can affect these three different things. So I'd like you to copy this out into your notes, guys. I'd like you to put a link if you think that the factors on the right affect the properties on the left. For example, the number of electron shells will certainly affect the atomic radius. That's a nice little thing to get you thinking about it. So pause the video, have a go at that, and then we'll go through some answers. So atomic radius is affected by the number of shells. We gave you that answer in this little blue thing here. But atomic radius will also be affected by the number of protons in the nucleus. If there are more protons, that means that the nuclear charge is going to be higher. That means that's going to affect the atomic radius. The higher the nuclear charge, and because of the number of protons, the smaller the atom. In terms of first ionization energy is also going to be affected by the number of shells. If there are more shells, then the ionization energy will decrease. If there are fewer shells, that means that those electrons are closer to the nucleus, they're harder to ionize. If there are more shells, that means that those electrons are further away from the nucleus, and therefore there's less attraction and it's easier to ionize them. It also depends upon the subshells, and you'll recall this from the atomic structure unit, where there is a pairing of electrons, then that affects the ionization energy, but it also is affected when you move from an S block, from the S block to the P block. So if you go from, say, 2s2 and move into 2p1, you'll see a slight jump in the ionization energy as you move through to another subshell. And we've already talked about pairs electrons, or the energy of a particular electron when you have to pair them. If you're pairing an electron, that takes slightly less energy to ionize it because there's a so-called repulsion energy. And all of this should be revision so far from what we've talked about way back in Unit 1. Linking in then with, I should also mention that it's to do with the number of protons in the nucleus, just as we've described for atomic radius as well. In terms of the melting and boiling points, the melting and boiling points really is just affected by the type of bonding you've got, whether it is ionic, whether it's covalent, whether it's metallic, but it's also affected by the structure. And just to think about covalent bonding has two types of structures. You can have simple covalent molecules, which are small, things like water and carbon dioxide. They have strong covalent bonds within the molecule, but they have weak intermolecular forces such as van der Waals or hydrogen bonding between the molecules, which means that they're liquids or they're gases. However, giant covalent structures, the bonding might be covalent, but the structure is giant, very, very large, with many, many bonds across a massive distance. There are no molecules, So therefore they have very, very high melting points. So the atomic radius depends on the number of shells and the nuclear charge. Why is there a slow, gradual drop? Here we've obviously got atomic radius in picometers, which is 1 × 10 to the minus 12. There's a scale here. There is a slow, gradual drop. Pause the video and have a think about the number of shells and the nuclear charge. So what we're seeing here is we're going across period 3, right? So as we're going across period 3, we're not adding in any additional shells. The nuclear charge is, however, increasing, right? So as we're not adding in any more shells, the shielding stays the same. Remember those effectively 3 factors that affect ionization energy. You're thinking about nuclear charge, atomic radius, shielding, and therefore all those impacts upon the attraction to the nucleus. The shielding is remaining the same because you're not adding in any further number of shells. So you'd expect that as you're not adding in any further shells, the atomic radius should be pretty much the same for all of these elements. However, the nuclear charge is gradually increasing. You're adding in an additional proton. By adding in an additional proton, that nuclear charge is going to increase, meaning that you are going to see a slight decrease in the atomic radius across the period. So the general trend is that the atomic radius decreases across a period, hence that little gradual drop that we're seeing. Okay, we've talked about shielding. Just to remind you, the inner electrons, the electrons that are closer to the nucleus, will repel the outer electrons. And what you're seeing as you go across a period is that you're not adding in any additional shells, right? You're keeping the number of electrons are always adding to the same shell. In this case, in period 3, the principal quantum energy level is the 3rd energy level. Therefore, you're not adding in any additional shells. So that isn't increasing the repulsion between those inner shells and the outer shells. Those electrons within the inner shells to the electrons in the outer shell. The shielding remains the same. So pretty much anyway, there's very little difference across a period. So we need to be able to explain atomic radius, and this all very much links in with Unit 1 atomic structure. So we've appreciated that as we go from sodium to argon, yes, the size of the atoms does decrease. However, they're roughly the same size because there's the same number of shells. And I'd like to stress roughly the same size. The size does decrease, but they're roughly similar. There's an increase in nuclear charge from sodium to argon. That means that there's a greater positive charge from the protons pulling on the electrons from argon, and so the atom is slightly smaller. Again, if you remember those 3 factors from Unit 1, the nuclear charge, the atomic radius, and the shielding, you can't go wrong. All impact the effective attraction between the outer electrons and the nucleus, which affects the ionization energy and indeed the size of those atoms. Okay, here's some 5 little statements about atomic radius. I'd like you to pause the video and try and work out if those statements are true or false. Number 1, the covalent radius is the distance between 2 identical atoms joined by a covalent bond. Is that true or false? Number 2, the atomic radius of period 3 elements decreases from sodium to argon. True or false? And number 3, increasing the number of protons, neutrons and electrons always increases the size of the atom. Number 4, the effective nuclear charge is the resultant attractive force from the nucleus experienced by the outer electrons. True or false? And finally, number 5, the effective nuclear charge decreases from sodium to argon due to increased shielding by extra electrons. I'd like to say that the effective nuclear charge is the charge experienced by the outermost electrons. This takes into consideration shielding. So pause the video and have a little think, true or false for each of the statements. If you could write them out in your notes, that would be brilliant. Here are the answers. Well done if you got them right. The covalent radius is the distance between two identical atoms joined by a covalent bond. There's no such thing as a covalent radius. The length of a bond is just known as the covalent bond length. Number 2, the atomic radius of period 3 elements decreases from sodium to argon. That is true because of the increased nuclear charge. The shielding effectively remains the same, so the atomic radius decreases. Increasing the number of protons, neutrons and electrons always increases the size of the atom. That is false. It depends upon the electron configuration, of course, and the amount of shielding. Neutrons don't affect the size of an atom, it's just protons and electrons because neutrons have no charge, they're neutral. Number 4, effective nuclear charge is the resultant attractive force from the nucleus experienced by the outer electrons. That is true, because it's just the outer electrons that we're considering in terms of the size of the atom. Number 5, the effective nuclear charge decreases from sodium to argon due to increased shielding by extra electrons. This is false because the shielding isn't increasing, you're not adding in any more inner shells. Well done if you got all those right. Okay, melting and boiling points. So the melting and boiling points depends exclusively on the type of bonding. So is it covalent? Is it ionic? Is it metallic? And the forces between the molecules, if there are molecules. That's why there is this phrase and or here. People often talk about forces between molecules when there are no molecules. Please be careful, Year 12. This is perfect revision of Unit 3 in terms of the structure and in terms of the bonding. Giant molecules or a metallic lattice, it's due to strength of metallic or covalent bonding. Remember, giant refers to the structure. It's large. Also, you can say the same of a lattice. If it's a lattice, it must be a giant structure. And then you've got the type of bonding as well. So the giant refers to the structure, how the atoms are arranged, and the bonding refers to what are the bonds between those atoms. Whenever you're answering a question like this, you need to think about the structure, how the atoms are arranged, and the bonding, what's holding the atoms together. You've then got simple molecules. Simple molecules have strong covalent bonds between those atoms within the molecules. However, the forces are weak between the molecules. So this in a nutshell gives you what you ought to be talking about in terms of thinking about the melting and boiling points. So thinking about period 3 then, which elements in period 3 are metallic? Which elements are macromolecular? Which elements will form simple molecules? And which elements are monatomic? Pause the video, have a little think, and as ever we'll go through the answers in a moment. Hopefully, Year 12, you got that sodium, magnesium and aluminium are metallic. Silicon, it would form macromolecules. It is a giant covalent structure. Simple molecules include phosphorus, which will form P4, S8 and Cl2, and monatomic is argon. Effectively, as you go across period 3, the bonding changes. On the far left-hand side of the periodic table are the metals. So in period 3, these are the metals. You'll recall that dividing line, that zigzag line that you drew in GCSEs to separate out the metals from the non-metals. So on the far left, sodium, magnesium and aluminium are metals. As you keep going, you get covalent. This is a covalent macromolecule. Silicon is right underneath carbon. It will behave very much like carbon then. Carbon, as we know, forms giant structures like diamond or graphite. Simple molecules, as you go further, such as phosphorus, silicon and chlorine. That's because in order to have a full outer shell, they will undergo simple covalent bonding to other atoms. So in the case of chlorine, it forms diatomic molecules. And for phosphorus and sulphur, you just need to remember that it's P4 and S8 are the most common allotropes of phosphorus and sulphur. Again, we'll talk more about this in year 13. And as we go to argon, argon is monatomic, of course, because it's unreactive. It won't react with other argon atoms, therefore it exists on its own because it's got a full outer shell and is therefore stable. So if you remember this order, you can remember these elements. The hardest thing is to remember P4, S8 and Cl2, but Cl2 you should know already from your GCSE studies. Okay, so if we plot this out on a graph where along the y-axis here we have the melting point in Kelvin, and then across the period here we have the atomic number and therefore the element. Sodium has an atomic number of 11. It is a giant metallic structure, so it has a relatively high melting point, not as high as you'd expect for a metal, but as we know, sodium it has weak metallic bonds. Generally, you can cut it with a knife. There's a big jump between sodium and magnesium because magnesium will form 2+ ions, and as a result, you'd expect the metallic bonding to be stronger, and indeed that's what you see. It's almost up to 1000 Kelvin. Aluminium, there's a slight increase. It's quite hard to see this here. Aluminium has ions with a 3+ charge, so you'd expect quite a larger increase. You'd expect, following this trend, aluminium to be something up here. It isn't quite, for reasons that we'll see later on. Silicon, being giant covalent, forming macromolecules, has the highest melting point of any substance in period 3. That's because it forms 4 strong covalent bonds to other silicon atoms. As we go down, there's a massive drop between silicon and phosphorus. Phosphorus forms P4 molecules. There's only going to be van der Waals sources of attraction between those molecules. Sulphur, it's slightly higher because it forms S8 molecules. That means there are more points of contact, there are more electrons, and therefore the intermolecular forces are stronger, hence why the melting point is higher. Chlorine Cl2 is smaller than sulphur and phosphorus, so its melting point and boiling point is lower, of that's phosphorus and sulphur. And argon, being monatomic, has the lowest melting point of any substance in period 3. You should have this particular graph in your resource booklet. Again, please make sure that you have labelled this up with the type of bonding. If you need to rewind to do so, please do. However, I'll just briefly go through it again, that these 3 here are metallic bonding, giant metallic. This here is giant covalent. These here are form small molecules, P4, S8, Cl2, and argon is monatomic. You need to be able to describe this graph in terms of the structure and bonding and how the structure and bonding influences the melting point. Okay, if you've understood that, you should be able to match up each type of bonding together with a melting point, together with some sort of explanation. In terms of your explanation, I've kept it very simple here. Remember that on an exam question, you need to talk about the structure and the bonding, and you also need to explain about the energy requirements to break those bonds, all those forces. I haven't talked about the energy here just for simplicity, but bear that in mind when you're answering an exam question. So pause the video and try and link these up, and we'll go through the answers in a moment. So metallic bonding has a relatively high melting point, as we've seen from our graph. That's because you've got a giant lattice. That means that all of the bonds between atoms have to be broken, which means that it requires quite a high amount of energy to do so. In terms of giant covalent, they have incredibly high melting points, silicon and carbon. Again, the same reason. The bonding is far stronger in covalent molecules. Each atom forms 4, in the case of silicon, 4 strong covalent bonds, so it has a very high melting point indeed, meaning that it's going to take a colossal amount of energy to break all of those bonds. Simple molecules have low melting points. You can probably guess the trend here now. That's because you only need to break the van der Waals forces between those molecules, P4, S8 and Cl2. The number of atoms in those molecules tells you the relative size of the melting point. S8 will be highest, then P4, then Cl2. The larger the number of atoms in a molecule, the more chance you have of forming van der Waals forces. There'll be more points of contact. That increases the melting point and indeed the boiling point. And then lastly, you've got monatomic atoms such as argon, which have very, very low melting points. Whilst argon has a great number of electrons, it's only one atom, so you only need to break the intermolecular forces, the van der Waals, and there are fewer opportunities to make those van der Waals forces with just one atom and a relatively low number of electrons as a result. So this is it, just written out in a slightly different order, just to make it a bit more friendly for your notes if you wish to rewrite it in your exercise book to get the right answers. Okay, let's have another little question then. If you've understood what I've been talking about, you can think about which element has the higher melting point. Is the melting point of phosphorus higher or lower than the melting point of sulphur? Pause the video and think about which it is, and maybe have a think about why that is the case. Okay, the answer is that the melting point of phosphorus is lower than that of sulphur. That would be a stating the answer, right? The explanation is this here, this bit that carries on a bit further. Phosphorus forms tetrahedral P4 molecules, while sulphur forms crown shape S8 molecules. As a result, in phosphorus, there were fewer points of contact. So that means that the van der Waals forces are weaker, and therefore, rather than saying easier to break, that's not really A-level language. What you ought to be saying, as hopefully you've recognised by now, is it's going to take less energy to overcome those van der Waals forces. Well done if you got that right, and especially well done if you got the correct explanation. Again, if you need to add to your notes to get the right answer, please do so. Okay, here is a graph of first ionization energy. Energy is on the y-axis here in terms of kilojoules. Along the x-axis, we have increasing atomic number, and therefore the different elements going from hydrogen all the way down to calcium, the first 20 elements. You'll have seen graphs like this before in terms of the atomic structure unit way back in September when we started A-level chemistry. So the first ionization energy depends upon the number of shells and the nuclear charge. It also depends upon the shielding, as we will see. And this really is a bit of a revision, reminding you about these. You'll recall, though, that this pattern here for period 2 is exactly the same for the pattern for period 3. If you look at where lithium is, lithium's above sodium, beryllium's above magnesium, boron's above aluminium, and so on. You see the exact same pattern, this zigzag pattern. The general trend is an increase in the ionization energy as you go across the period. That's because the nuclear charge is increasing. There are, however, dips between beryllium and boron, and between nitrogen and oxygen, right? And we need to be able to explain that. The same situation is true from magnesium to aluminium and from phosphorus to sulphur. You need to be able to explain those dips. So this is just for period 3 because this is what this unit is about, but I wanted to draw the parallel to period 2, which we covered way back in Unit 1. So again, we see this trend, and you should be able to sketch this graph out in an exam. Very, very simply. You don't obviously need to know the specific numbers here, but you do need to know the trend. So the general trend, as we know, is that the ionization energy increases. However, there are these little exceptions, as we've discussed. The exceptions are for aluminium and for sulphur, where there is a dip. The ionization energy is lower than we would expect, given that we said the general trend is a general increase across period 3. So if we compare aluminium and magnesium, that first dip, the first ionization energy of aluminium is lower than magnesium, even though aluminium has a much higher nuclear charge. Magnesium obviously having a nuclear charge of +2, aluminium having a nuclear charge of +3. If we think about the electronic structure though, in terms of these box diagrams, remember that each box represents an orbital, right? And each electron is represented by an arrow, and that arrow can either be spin up or it can be spin down. And we need to think about the Aufbau principle, building up from the ground up, and Hund's rules, and also the Pauli exclusion principle, again that we learned way back in Unit 1 in atomic structure. If we think about aluminium compared to magnesium, aluminium has an identical electron structure to magnesium up until that final electron. That final electron is going into a 3p orbital. As a result, it's going to take less energy to remove that 3p electron because it is in a slightly higher energy level compared to the 3s, because these are sub-levels, sub-shells. So just to put that into words, removing an electron from a higher energy orbital requires less energy. So the 3p, it's easier to ionize an electron from a 3p orbital compared to a 3s orbital. As well as this, we need to think about the shielding. And because it's going into a higher energy orbital and the 3s is at a lower energy orbital, these electrons here will shield out the nucleus for that 3p electron, compounding the situation, making it even easier to remove that 3p electron. Okay, carrying on then, the second dip that we see is between phosphorus and sulphur. And the first ionization enthalpy of sulphur is less than that of phosphorus, even though sulphur has a higher nuclear charge. So let's draw out those electron configuration diagrams again. And we see that the electron configuration for phosphorus and sulphur is indeed very, very similar. The only difference is that sulphur, having 3p4 as opposed to 3p3, you have to pair up this electron into the 3px orbital. That takes a certain amount of energy to do so because you're putting an electron in the same orbital, and those electrons will repel each other. Remember that this has a spin down orientation because of the Pauli exclusion principle, that no two electrons within the same orbital can have all of their quantum numbers the same. So to get round that, it has to have a spin of -1/2 compared to a spin of +1/2. That takes a certain amount of energy, and that repulsion means that that electron is far easier to remove than, say, this electron. So putting it into words, mutual repulsion between paired electrons means that less energy is required to remove that electron. So where electrons are paired up, the fact that they're repelling each other means that there's less energy needed. Please can you make sure that both of those cases are highlighted in your notes and that you've written that down really, really well. Hopefully my explanation helps with that. So we need to think about how we can explain ionization energies. Electrons are in the same shell, so you'd expect them to be the same distance from the nucleus, whereas we go from sodium to argon. However, there is an increase in the nuclear charge. Sodium has 11 protons, whereas argon has 18. So that means that there's a greater positive charge from the protons pulling on the electrons for argon, so it's harder to remove that electron. The attraction is higher. There are two exceptions, as we've discussed, that magnesium has a full s orbital, so removing the higher energy electron from aluminium is easier, and that phosphorus has a half full p orbital, so removing the paired electron from the sulphur is easier because of the subshells and because of the repulsion between those electrons that are paired up within the same subshell. In one slide, this is a nice little summary of everything that we've talked about. Hopefully this all makes sense. So, what have we learned today? Hopefully you can write down 3 bullet points on what you've learned in this particular video lesson. You can do that in your unit guide. Please make sure that you do update your unit guide. Remember that you can access these on the VLE, particularly the what, how section and the checklist, because it's not only important as in what you're learning, but how you're learning it, and in terms of what you need to improve, as well as how you will improve is really important. You also can fill in the checklist first, those little tick boxes. That might help you to think about areas where you're not so confident. You can also self-mark the past paper section once it's complete, because this unit is very, very short and sweet. Everything in this video lesson encompasses all of those learning objectives in the front of the unit guide, and the mark scheme is available on the VLE. If you're having any problems or difficulties, Year 12, you know precisely where to find me. Please don't hesitate to contact me. I'll make sure that this is incorporated with a little quiz on Microsoft Teams for you to be working through. Again, any problems, please do send me an email or message me through Teams. Thank you for your attention. Have a lovely afternoon, or indeed evening.